Welcome to the Cosmic Frontier, where today we're diving into the latest breathtaking revelation from the James Webb Space Telescope, JWST. In this video, we explore a shocking discovery that could potentially hint at a hidden exomoon orbiting a failed star, also known as a brown dwarf. Stay with us as we unravel the layers of this cosmic mystery and what it might mean for our understanding of the universe. The James Webb Space Telescope, JWST, has unveiled a stunning revelation in the cosmos: methane emissions emanating from a brown dwarf, commonly referred to as a failed star. This intriguing discovery not only challenges our understanding of these cold, solitary celestial bodies previously thought too frigid for methane to emit infrared light, but also hints at the presence of aurorae and the exciting possibility of an unseen exomoon orbiting this enigmatic object. Researchers are buzzing with the implications of these findings, which could reshape our knowledge of the complex behaviors and conditions within brown dwarfs. The remarkable discoveries were made through a dedicated James Webb Space Telescope, JWST program that studied 12 brown dwarfs. This research indicates that these enigmatic failed stars are capable of generating dazzling aurorae, akin to Earth's mesmerizing northern and southern lights, and those observed on Jupiter and Saturn. Intriguingly, the isolation of this particular brown dwarf, with no nearby star to influence it, suggests that the mystical auroral displays could be the work of a concealed, active moon orbiting it. This revelation adds a thrilling layer of mystery and complexity to our understanding of celestial phenomena. The research team delved into the mysteries of the cold brown dwarf known as CWISAP Zone 193,518.59, 154,620.3, 1,935, which is situated 47 light-years away from Earth. The mass of W1935 is not well defined, fluctuating between 6 and 35 times that of Jupiter, yet it boasts a surface temperature of about 400 degrees Fahrenheit, 204 degrees Celsius. Coincidentally, the same temperature you might use to bake chocolate chip cookies. This phenomenon highlights the ever-evolving nature of space exploration and the surprises that lie in the universe's vast expanses. What makes some stars fall short of their stellar destiny? Brown dwarfs, often termed failed stars, emerge from the same cosmic recipe as stars, a collapsing cloud of gas and dust. However, they lack the critical mass required to ignite nuclear fusion from hydrogen to helium in their cores, the defining process of a main sequence star. Positioned in a cosmic limo, brown dwarfs carry more mass than the mightiest planets, but not enough to match the smallest stars, thereby missing the mark of becoming full-fledged stars. During their observations with the James Webb Space Telescope, JWST Faherty and her team were studying various brown dwarfs when they encountered something exceptional about 1935. It was emitting methane, a phenomenon previously unobserved in such objects. Further analysis of W1935 uncovered another astonishing feature: a temperature inversion in its atmosphere, where temperatures decrease at deeper levels rather than increase, typically seen in planets with atmospheres heated from above by their stars. This was a surprising find in an isolated brown dwarf without any external heat sources. We were astounded when our models not only confirmed the presence of a temperature inversion, but also posed a tantalizing question: what was heating the upper atmosphere? Remarked Ben Birmingham, a scientist at the University of Hertfordshire. This unexpected twist adds a layer of intrigue as the team continues to unravel the mysterious heating mechanisms at play in the cold reaches of space. To unravel the enigma of the brown dwarf 1935, researchers turned their attention to familiar celestial bodies within our own solar system, Jupiter and Saturn. Both of these gas giants are known for their methane emissions and exhibit temperature inversions in their atmospheres. For Jupiter and Saturn, aurorae are the culprits behind both the methane emissions and the atmospheric temperature inversions. This led Faherty and her team to an intriguing hypothesis: The unusual phenomena observed around W1935 might also be due to aurorae. The question then became, what powers these aurorae on W1935? Typically, aurorae on planets like Jupiter, Saturn, and Earth are driven by solar wind, which is a stream of charged particles from the Sun. These particles interact with the planet's magnetic field, travel along the field lines, and collide with atmospheric particles, heating the upper atmosphere and producing the spectacular light displays near the poles. However, W1935 lacks a host star to provide solar wind, suggesting that something else must be driving its aurora. On Jupiter and Saturn, a secondary, less dominant mechanism involves charged particles released from active moons, such as Jupiter's volcanic moon Io and Saturn's geyser-spouting moon Enceladus. These moons eject materials such as lava and water vapor into space, contributing to the auroral activity on their respective planets. This analogy presents a fascinating possibility. W1935 might also be orbited by an active moon, which could be responsible for the auroral phenomena observed. This scenario, if confirmed, would mark a significant discovery in understanding isolated brown dwarfs and the dynamic interactions within their systems. Further research is essential to definitively confirm the presence of a moon orbiting a brown dwarf for the first time. In the meantime, these preliminary findings highlight the transformative impact of the James Webb Space Telescope, JWST, which has been revolutionizing our view of the universe since it began transmitting data back to Earth in the summer of 2022. Every observation with the JWST presents a potential for groundbreaking discoveries, Faraday reflected. Methane emission was unexpected when we embarked on this project, but now that we've seen its potential and the intriguing explanation behind it, I find myself eagerly anticipating its presence in future observations. This constant state of discovery is a driving force in advancing scientific knowledge. The James Webb Space Telescope, with its unparalleled observation capabilities, has made a potentially groundbreaking discovery. Scientists analyzing data from JWST have noticed anomalies that suggest the presence of an exomoon. This celestial body is believed to be orbiting a brown dwarf, a star-like object that failed to ignite due to insufficient mass. Let's delve into the details of this discovery and its implications. Before we proceed further, let's clarify what a brown dwarf is. Brown dwarfs are substellar objects that sit in the cosmic limbo between the largest planets and the smallest stars. They lack the necessary mass to sustain hydrogen fusion reactions at their cores, which is the process that powers stars like our Sun. Understanding these failed stars is crucial as they bridge the gap in our knowledge between stars and planets. Exomoons are moons that orbit exoplanets, or, in this rare case, potentially a brown dwarf. Their study is relatively new, but incredibly significant. Exomoons can provide critical clues about planetary formation and evolution in the cosmos. They might also affect the habitability of their parent planets, making their study crucial for understanding the potential for life elsewhere in the universe. The potential discovery of an exomoon around a brown dwarf is exciting for several reasons. It challenges our current understanding of how moons and planets form and evolve. It also opens up new avenues for studying atmospheric conditions and gravitational interactions in extreme environments, providing a new layer of depth to our cosmic knowledge. This discovery paves the way for future observations and research. With JWST's capabilities, we can expect more detailed studies on the properties of these elusive celestial objects. The implications for astrophysics are profound, as each discovery potentially leads to more questions and a deeper understanding of the universe's most fundamental processes. Detecting exomoons, especially around brown dwarfs, poses significant challenges. The faintness of these objects, combined with the vast distances involved, makes observations extremely difficult. Technologies like JWST utilize advanced optics and infrared capabilities to pierce through cosmic dust and capture these elusive signals. We'll discuss the technological marvels that make such discoveries possible. The search for exomoons is not new, but it has gained momentum with recent advancements in telescopic technology. Comparing past discoveries can help us appreciate the groundbreaking nature of detecting an exomoon around a brown dwarf. This segment will provide a brief history of exomoon research and how it has evolved over the years. Infrared astronomy is crucial when studying objects like brown dwarfs and potential surrounding exomoons. The James Webb Space Telescope's infrared capabilities allow astronomers to detect heat signatures and other indicators that are invisible in the optical spectrum. This segment explores how infrared technology works and why it's so important for these kinds of astronomical discoveries. How do moons form, especially in unconventional systems like around a brown dwarf? This segment delves into the current theoretical models of moon formation, including the capture theory, impact scenarios, and co-accretion. Understanding these models helps scientists predict and interpret observations of potential exomoons. Each new discovery has the potential to reshape our astrophysical theories. Finding an exomoon around a brown dwarf could challenge or confirm existing theories about stellar and planetary formation and dynamics. This segment discusses how new findings might integrate with or disrupt current scientific consensus. What are the next steps following this intriguing discovery? This segment outlines the proposed observational campaigns, data analysis techniques, and theoretical studies that scientists plan to pursue to confirm and understand the nature of the suspected exomoon and its brown dwarf host. Large-scale astronomical discoveries are rarely the work of a single entity. This segment highlights the collaborative efforts behind the scenes, including partnerships between different observatories, universities, and international space agencies. Understanding these collaborations can give us insight into how complex scientific discoveries are made. Discoveries like these have the power to inspire the public and educate people about science and our universe. This segment will discuss how institutions and educators use these exciting discoveries to engage with the public and students, sparking interest in STEM fields. Beyond the science, the discovery of an exomoon around a brown dwarf raises philosophical questions about our place in the universe and the nature of celestial objects. This segment explores the broader implications of such discoveries on our understanding of life, existence, and the cosmos. This segment dives into the specific observational techniques used by the James Webb Space Telescope to detect signs of exomoons. These techniques include transit photometry, radial velocity measurements, and direct imaging, each providing unique insights into the characteristics of these celestial bodies. We'll explain how these methods work and their importance in the field of exoplanetary science. Once data is captured by telescopes like JWST, the next critical step is analysis and interpretation. This segment covers the sophisticated software and algorithms that astronomers use to sift through massive amounts of data to identify potential exomoons. We'll explore the challenges of distinguishing actual celestial phenomena from noise and the role of artificial intelligence in modern astronomy. Comparative planetology allows scientists to study and compare different planetary systems, including those with brown dwarfs and their moons. This segment discusses how comparing these systems helps scientists understand planetary formation, atmospheric compositions, and potential habitability. Insights gained from systems like the one possibly featuring an exomoon can be pivotal. Behind every major astronomical discovery is a framework of funding and support. This segment explores how projects like the James Webb Space Telescope are funded, including the roles of governmental agencies, private sectors, and international cooperation. Understanding the financial aspects can provide insights into the challenges and opportunities in space research. Confirming the presence of an exomoon, especially around a brown dwarf, is fraught with challenges. This segment discusses these challenges, including the need for repeated observations, the requirement for high-precision data, and the lengthy periods over which data must be collected. We'll also look at the criteria used to validate such findings. The discovery of an exomoon around a brown dwarf could have significant implications for future space missions. This segment considers how current findings might influence the design and objectives of future telescopic missions, including the focus on specific types of celestial bodies and the development of new technologies aimed at better understanding our universe. Significant discoveries often capture public interest and receive extensive media coverage. This segment explores how such discoveries are reported in the media and their impact on public perception of space exploration. It also considers the role of astronomers and scientists in communicating their work to the public to foster a better understanding of their significance. Discoveries like these also have profound implications for education, particularly in the sciences. This segment discusses how new findings are integrated into educational curricula and public science programs, potentially inspiring the next generation of astronomers and scientists. As we push the boundaries of what is known, ethical considerations become increasingly important. This segment delves into the ethics of space exploration, including the treatment of data, the sharing of findings with the international community, and the long-term implications of expanding human knowledge and presence into space. This segment examines the interdisciplinary collaborations that are essential in modern astronomical discoveries. Teams comprising astronomers, physicists, engineers, and data scientists work together to solve complex problems posed by the universe. We explore how these diverse fields converge in projects like the James Webb Space Telescope, enhancing our ability to discover and analyze distant celestial phenomena. Advancements in astronomy often spur innovations in technology. This segment delves into the technologies developed specifically for space exploration and how they have found applications in other industries, such as telecommunications, imaging technologies, and computational methodologies. We'll look at how these innovations not only aid in scientific discovery, but also benefit society at large. One of the most captivating aspects of discovering exomoons and exoplanets is the possibility of finding extraterrestrial life. This segment discusses how the discovery of an exomoon around a brown dwarf could impact the search for life beyond Earth, considering the potential for these moons to harbor conditions suitable for life and the scientific methods used to detect such possibilities. Space exploration is a global endeavor. This segment highlights the importance of international cooperation in such projects, discussing the roles of various international space agencies in the James Webb Space Telescope and other similar missions. We consider how collaborative efforts not only pool resources, but also foster peace and mutual understanding between nations. Discoveries in space have a profound impact on culture, influencing everything from art and literature to philosophy and public discourse. This segment explores how new findings about the universe influence our cultural narratives and inspire creativity across various mediums, reinforcing the deep human connection to the cosmos. As our capabilities to explore space expand, so too does the need for robust legal and policy frameworks. This segment examines the existing laws governing space exploration and how they might need to evolve in response to new discoveries and technological capabilities, including the management of space traffic and the protection of celestial bodies. This segment addresses the challenges associated with data sharing and accessibility in the field of astronomy. With the increasing amount of data being generated by telescopes like JWST, ensuring that data is accessible to researchers around the world is crucial. We discuss the policies, technologies, and collaborations that support data sharing and how they impact scientific progress. Looking forward, this segment speculates on the future technologies that could revolutionize astronomy further. Innovations such as more powerful telescopes, AI-driven data analysis, and space-based observatories could dramatically enhance our understanding of the universe. We explore what is on the horizon and how these technologies might come to fruition. As space exploration advances, sustainability becomes an increasing concern. This segment considers the environmental impact of launching spacecraft and maintaining observatories, both on Earth and in space. We discuss initiatives aimed at making space exploration more sustainable, including minimizing space debris and utilizing resources found in space. As space exploration becomes more accessible, the prospect of space tourism and commercial ventures looms larger. This segment explores the burgeoning industry of private spaceflight companies and the role they play in advancing space exploration. We discuss how these ventures contribute to the broader goals of scientific discovery while also fueling public interest in space. Citizen science initiatives empower individuals to contribute to scientific research, including in the field of astronomy. This segment discusses how citizen scientists can aid in the discovery and analysis of exoplanets, exomoons, and other celestial bodies. We explore platforms and projects that engage the public in meaningful astronomical research. Space exploration not only expands our scientific knowledge, but also influences society in profound ways. This segment examines how space exploration shapes culture, technology, and global cooperation. We discuss the societal benefits of space research and the ethical considerations that arise as we venture further into the cosmos. The dream of colonizing other worlds and traveling to distant stars has captured the human imagination for centuries. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.